Okay, in this example, we'll do an example of orthogonal diagonalization. So the theorem is that if you have a symmetric matrix, if A is a symmetric matrix, okay, let's just recall that that means that A transpose is equal to A. So if A is a symmetric matrix, then A is what's known as orthogonally diagonalizable. And what does that mean? It means that there is an orthogonal matrix P. Okay, let's use Q. That's more typical for orthogonal matrices. Orthogonal matrix Q and a diagonal matrix capital lambda such that A is equal to Q lambda Q inverse. Okay. So diagonalizable just means that there's an invertible matrix P such that A is P times lambda times P inverse. But the new twist is that the P matrix is, well, you can make it so that it's orthogonal, right? So, you know, there's lots of P's, there's lots of matrices P such that A is equal to P lambda P inverse, but there is a P that is orthogonal. That's what's going on. And just let's recall that an orthogonal matrix is a matrix such that, well, it's invertible and also its transpose is equal to its inverse. So I could also have written, you know, Q lambda Q inverse as Q lambda Q transpose because Q inverse is equal to Q transpose. Okay, and then one more thing maybe is that in a lot of books, this diagonal matrix is written as D, and in the videos that I have on diagonalization, I use D, but it's actually, I like to use lambda to indicate that lambda is a matrix whose diagonal entries are eigenvalues, the eigenvalues of A. Okay? And this is a symmetric matrix with real entries. So we're not talking about complex numbers. This is all the entries of A are real. And yeah. So that's the theorem. And in this video, we're not going to prove it, but we're going to give an example of how it works. So maybe before going on, I should mention that being an orthogonal matrix is equivalent to the columns are unit vectors and the columns are mutually orthogonal. Okay, so this condition. All right, let's do an example of coming up with an orthogonal diagonalization. And in this example, I designed it to be relatively easy. So orthogonally diagonalize the matrix A, which is, the rows are 3, 2, 1, 2, 3, 1, and 1, 1, 4. Well, we basically are going to diagonalize the matrix, and then once we diagonalize the matrix, we just need to adjust the matrix P that we get so that you get unit length columns, and yeah, okay. It turns out that this matrix will have distinct eigenvalues, no repeated eigenvalues, and for a symmetric matrix, it turns out that the eigenvalues, if you have two different eigenvalues and you take an eigenvector for each of those eigenvalues, those two eigenvectors you get will be automatically perpendicular, will be automatically orthogonal. We'll see that in this example. All right, so we're just going to diagonalize this matrix. So first we need to find the eigenvalues, right? And for this, we need the characteristic polynomial. So we need the determinant of a minus lambda I. And I'm going to skip the step because it's very complicated. You have this, you're going to have to take a determinant of 3 by 3 matrix. And it's going to have a bunch of terms, and you have to distribute the whole thing, and then you have to factor the whole thing. And I'm just going to skip all that because it will take, I actually did it all. And it turns out that it ends up being negative, parentheses, lambda minus 6, lambda minus 3, lambda minus 1. And so therefore the eigenvalues of A are lambda 1 is 6, lambda 2 is 3, and lambda 3 is 1. Also, I'm going to use the convention when ordering the eigenvalues that they go from largest to smallest. So here they go in the order 6, 3, 1. Of course, you could make it in the order 1, 3, 6, 1, 6, 3, whatever order you want, but just as a convention, it's typical to order the eigenvalues from largest to smallest. Okay. And so here we have 3 distinct eigenvalues, right? And so the dimension of the eigenspaces will be 1. So what's going to happen is, we already know what's supposed to happen. We're going to find, for each eigenvalue, we're going to find a one-dimensional eigenspace, and so we're going to get one linearly independent eigenvector for each of the eigenvalues. Okay, and if we don't, that means we messed up the arithmetic. So now we need to find the eigenvectors. Let's do lambda 1 first. And here I'm actually going to do all the steps. So we do a minus lambda I, so that's a minus 6i. And if you look at the matrix above and take away 6 on the diagonal entries, you get negative 3, 2, 1, 2, negative 3, 1, 1, 1, negative 2. Now we're trying to find the null space of this matrix, right? That's the eigenspace with the eigenvalue 6. And so we need to solve a minus 6i times x equals 0. And so, well, what's going to happen when you set up the augmented matrix is I'm going to do a row exchange. I'm going to exchange rows 3 and 1. So I'm going to get this. Now we're solving a homogeneous system. So the augmented column is always going to be 0, 0, 0, right? And so, technically you don't even have to write it down because you know it's going to be 0, 0, 0 every single time. But just to maybe emphasize the fact that what we're doing is solving, a minus 6i times x equals 0, I'm just going to leave this column. Okay. It's just to make it clearer what's going on if you're referring to this as notes. So anyway, so now we row reduce, so I'm going to do row 2 minus 2 row 1 and row 3 plus 3 row 1, right? I'm using my pivot 1 on the top to make the numbers below the 1 equal to 0. And when you do that, you're going to get 1, 1, negative 2, 0, negative 5, 5, 0, 5, negative 5. And that's exactly what we want, because now you do row 3 turns to row 3 plus row 2, and you're going to get a row of zeros, which is exactly what should happen. because remember, we're going to get a non-trivial solution. And I see I have 2 pivots, and so my null space is one-dimensional, which is exactly what should happen. So now here we're just going to get this into reduced row echelon form. We divide row 2 by -5. So you're going to get this. And then the last step is I want this 1 to be a 0, right? So I do row 1 minus row 1 turns into row 1 minus row 2. So it's going to be so I do -2 minus -1, that's -2 plus 1, that's -1. So I get this. And now we're ready to find the eigenvectors, so we write out the equation. Let's just use x, y, and z as the variables. So x minus z is 0, y minus z is 0, right? I'm getting that from these 2 rows. And so this tells me that x is equal to z, y is equal to z, and of course z is our free variable, z is equal to z. And so we get that the solution, x, y, z, is just z times 1, 1, 1. Kind of messy. I mean, I could use t instead of z, whatever. The point is that my eigenvector is v1 is 1, 1, 1. And of course I can take any scalar multiple of that, as long as it's a non-zero scalar multiple, and I'll get an eigenvector. But I want this to have unit length, and this does not have unit length. Its length is root 3, right? So I need to divide by the length. And so I'm going to get a unit vector, let's call it u1. And so I divide by root 3, 1 over root 3, 1 over root 3, 1 over root 3, and then this is going to have unit length. All right, now I just do the same thing. So that's the first column of my matrix Q. Now we need to do the same thing for the other eigenvalues. Okay, let's continue. So then for lambda 2 is 3, we just do the exact same thing. A minus 3i is 0, 2, 1, 2, 0, 1, 1, 1, 1. Now you see why we have software to do this. So let's see, we're going to swap rows 3 and 1 again. And you're going to get this. So remember what we're trying to do is we're trying to solve a minus 3i times x is 0. So we're solving this homogeneous system. Okay, row, at least we have a 0 in the 3 1 entry. So that cuts down our steps. So we just do row 2 minus 2 row 1. Turns into the new row 2. So it's going to be 0, negative 2, negative 1, 0, 0, 2, 1, 0, and good. Our last row is, in fact, going to be a row of zeros, which is exactly what we want. That's what it should be, because we know that our solution space is one-dimensional. Okay, so now we have this, and now, all right, so we have one free variable, and then let's just convert this into reduced row echelon form. Oops. So let's make this negative 2 into a 1, so row 2 divided by negative 2. So you get this. And then the last step is row 1 turns into row 1 minus row 2. So then you get this. And now our matrix is in reduced row echelon form. So now we write down the equations. X plus 1/2 z is 0. Y plus 1/2 z is 0. Z is just z. So this is going to give you x is negative 1/2 z. y is negative 1/2 z, z is equal to z. So then x, y, z is just z times negative 1/2, negative 1/2, 1. So we can make our v1, well, our v1 can be equal to this. Okay, that's totally fine, and we just normalize by dividing by the length. But we can take any scalar multiple of v1, right? We're just trying to come up with one eigenvector. So why don't we just get rid of the fractions and multiply that vector by 2, and so let's take v1 to be negative 1, negative 1, 2. And now we normalize this by dividing by the length. The length is the square root of 6, right? Because you just take each of the individual components, square them, add them up, and take the square root. So negative 1 squared is 1, negative 1 squared is 1, 2 squared is 4, 1 plus 1 plus 4 is 6, and then square root is 6. So then you just divide each of the components by root 6. And now we have an eigenvector which is unit length. Oh, let's call this v2, right? So that's going to be the second column of Q. All right, finally, we have one more eigenvalue. Lambda 3 is 1. So we're just going to do a minus I, and that gives you 2, 2, 1, 2, 2, 1, 1, 1, 3. Now I see that I'm going to swap I can swap rows 1 and 3 again, and then, okay, I can just do row 3. Okay, this is going to turn into, right, what I'm going to get is, okay, if I really show it all the steps and do the algorithm properly, I'm going to swap rows 3 and 1 and do this, and then do row 2 minus 2 row 1 and row 3 minus 2 row 1. And so if I do that, I'm going to get 1, 1, 3 on the top, and then 0, 0, negative 5, right? Because it's row 2 goes to row 2 minus 2 row 1. Yep, and then I'm going to get the same thing here. And then now I forgot the row 0, the column of zeros, whatever. I don't really need that. Okay, because it's just going to be the column of zeros anyway. So now you have this, and then row 3. This isn't an echelon form yet because I have 2 pivots. Right? I have these numbers here, but I want this negative 5 below it to be 0. So I do row 3 goes to row 3 plus row, row 3 goes to row 3 minus row 2, and that will give me this. And now I just need to, I already see what I'm going to get in the reduced row echelon form. Okay, but to show it all the steps, I'll divide negative 5 by negative 5 to get 1, right? Okay, now I'll do the column of zeros, and then row 1 goes to row 1 minus 3 row 2, so I get this. So that's my reduced row echelon form. Okay, so now I write down the equations. X plus y is 0, z is 0, and then this tells me that x is negative y. So my free variable this time is actually y, right? So y is equal to y, z is equal to 0. So this tells me that x, y, z is equal to y times negative 1, 1, 0. And so my v3 is negative 1, 1, 0. But I'm trying to come up with, again, a unit length vector, so I need to divide by the length. And the length is the square root of 2, so now it's negative 1 over root 2, 1 over root 2, 0. And so finally, I have my u3, I have my u2, and I have my u1, and I make those the columns of Q. So now Q is going to be, okay, what was u1 again? Okay, 1 over root 3, 1 over root 3, 1 over root 3. u2 is negative 1 over root 6, negative 1 over root 6, 2 over root 6. And then u3 is negative 1 over root 2, 1 over root 2, 0. So that's my Q, and then my lambda is the matrix with the corresponding eigenvalue, 6, 3, 1. Okay, so if Q is that and lambda is that, then it turns out that A is equal to Q lambda Q inverse. And notice I have unit length vectors, but I needed the columns to be orthogonal to each other. But it turns out that if you take the dot product of the first two columns, you do in fact get 0. And if you take the dot product of the first and third columns, you do in fact get 0. And if you take the dot product of the second and third columns, you do in fact get 0. So Q really is an orthogonal matrix. But notice that we didn't have to do, this goes back to the comment I made earlier, we didn't have to actually do anything to the columns to make them orthogonal. When we just found the u1, u2, and u3, they were automatically orthogonal. And that's because there's a fact that if you have eigenvectors corresponding to distinct eigenvalues of a symmetric matrix, a real symmetric matrix, then the eigenvectors are automatically orthogonal. Okay, what happens if you have, so here our characteristic polynomial has 3 distinct roots, right? So you have 3 distinct eigenvalues. But you could have had something like, it's a different color. Maybe like negative lambda minus 3 squared, lambda minus 1. And then you'd have a repeated eigenvalue. And when you have a repeated eigenvalue, so in this case, you have a repeated eigenvalue of 3, and the dimension of the eigenspace is 2, so you have a 2-dimensional eigenspace. And what you have to do to produce an orthonormal basis is to use the Gram-Schmidt procedure. So there's something called the Gram-Schmidt procedure, and that's a way to produce an orthonormal basis, and that's what you would have to do to produce the Q if your characteristic polynomial has a repeated root. Okay, maybe I'll make a video of that. I don't have a video on Gram-Schmidt yet, but anyway, if you just look in a linear algebra textbook, you'll do some examples of this. Okay, so this is a very tedious example, but I wanted to do one example all the way just to illustrate exactly how you do it. And then maybe one more comment is that you do have some leeway in your Q matrix. Well, first of all, you can always rearrange, right, the order in which you write down the eigenvalues. And in that case, there's like 6 possible ways to arrange the 3 numbers. In that case, you can just rearrange the columns to match that. Okay, so you do have some leeway in your Q and your lambda, but you need these vectors. See, in this case, you have 3 distinct eigenvalues. In this case, right, you really only have a one-dimensional eigenspace for each eigenvalue. So, and you want your eigenvector to be a unit vector, and so the only way to do that, once you have an eigenvector, the only way to do that, to make a unit length one, is to scale it so that it's, say, this vector, but then you can also multiply by -1, right? So, once you have a unit length eigenvector, say u, then the only other eigenvector that's in the same direction as u, that's like in the span of U is negative U, and that's the only other unit length vector. So you can always multiply each of these columns by -1. That's going to give you a different Q, but it'll also still work. Okay, so I hope you found this example helpful. I'm probably going to make another video where I use this example matrix to illustrate something called a constraint optimization, and then I'll need the fact that the A matrix decomposes like this. Okay, thanks.